Hello, welcome back to Smart Bookhead's online YouTube channel. If this is your first time of coming to our channel, please don't forget to subscribe and also on our notification icon so that you will be notified whenever we release a new video. So we have a problem which goes as follows. An adiabatic cylinder sketched below contains nitrogen gas model as an ideal gas and a block of copper separated by an adiabatic membrane. Initially state 1. The pressure and the temperature of the gas is 6 times 10 raised to the power of 5 Pascal and 270 Kelvin respectively. The copper block temperature is 380 Kelvin. A heavy adiabatic frictionless piston with mass 45 kilogram is pinned at a height of 20 centimeter above the surface of the copper block. The copper block is 1 centimeter thick. The surface area of the piston is 50 centimeters square. The density of the copper is 8.96 grams per centimeter cube. And the specific heat capacity of copper is 385 joules per kilogram Kelvin. The gas constant of nitrogen is 297, and the specific heat capacity of at constant volume is 741 joules per kilogram Kelvin. So assuming pressure is 0 absolute outside the cylinder, so we are asked to obtain the mass of nitrogen gas and also the mass of copper. Let's start with the above two first. So now to calculate the mass of the nitrogen gas, we already know that the gas is modeled as an ideal gas, so therefore we can use the ideal gas equation, which says the product of pressure and volume is equal to the product of the mass, molar gas constant, and temperature. So from the formula we can see that we have our mass, which we can make the subject of formula, and it will equals PV over RT. So from our question we're given the initial value of our nitrogen pressure and also the temperature. This is the nitrogen pressure and this is the temperature at the same time, so which means that we have our P to be equal to 6 times 10 raised to the power of 5 Pascal, and we also have our temperature to be given directly to be 270 Kelvin. So our R is also given, which is 297 joules per kilogram Kelvin. So what is missing from our formula is only volume, and this volume can be obtained from our cylinder. The volume of cylinder is going to be equal to the volume of our gas, the portion that we are going to calculate. So from here to here is occupied by our gas, and it has a height of 20, and we're given that the area of our piston is 50 centimeter squared. So therefore we can say that volume is equal to the area multiplied by the height, but area is given of that of the piston, which is the same of the container, which was given to us as 650 centimeter squared. So let's convert this to meter. We just go ahead and multiply this by 10 raised to the power of minus 4. This is going to give us 5 times, so we are going to have 5 times 10 raised to the power of minus 3 meter. Also our height is given to be equal to 20 centimeter. So this can be calculated as converted to meter as 0.2 meters. So therefore we now have our volume to now be equal to 5 times 10 raised to power of minus 3 times 0.2. So upon computing that, we're going to have 1 times 10 raised to power of minus 3. So this is our volume. So since we are having our volume, then our mass is going to be the pressure, which is 6 times 10 raised to power of 5 multiplied by the volume, which is 1 times 10 raised to power of minus 3, all over our R is given to be 297 multiplied by, we have our temperature to be 270. So therefore the mass of our nitrogen gas is now equal to, upon computation, we are going to arrive at 7.482 times 10 raised to power of minus 3 kg. So this is the mass of our nitrogen gas. So we have calculated the mass of our nitrogen gas. Now we can go ahead and calculate the mass of our copper, which was asked here from our question. So to do that, since we're given the density of copper, then we can go ahead and calculate the mass of our copper. So from this formula we're given, we can say that mass is now equal to rho v. So again, volume is not given, we have to calculate it. The volume of our piston is A, which can be also taken as the volume of our copper multiplied by the height which our copper occupies. So this is the height which our copper occupies, which is 1 centimeter. So height of our copper is 1 centimeter, which is equivalent to 0.01 meter, and our area as usual is equal to 50 centimeter squared. So here volume is now equal to the area, which is 50. I will use it without converting it, multiply by 0.01. So this is going to give us the volume is going to be 5 times 10 raised to the power of minus 5 meter cube. Upon conversion, we have already converted this while we are computing for our nitrogen gas. So therefore our mass is equal to our density. Our density too, we need to convert it. So sorry, let's convert the density first. So our density is equal to 8.96 grams per centimeter cube multiplied by 1 kg all over 1000 grams. So 1 kg over 1000 grams is just like multiplying by 1, and then multiply by 1000, sorry, multiply by 100 cube all over 1 meter cube. So 100 centimeter cube is also equivalent to 1 meter cube. So it is as though we are multiplying by 1. So our density will now be found to be 8,960 kilogram per meter cube. So our mass will now become 8,960 times our volume, which is 5 times 10 raised to the power of minus 5. So our mass will now be computed as 0.448 kilogram. So this is part A. Part B of the question. So moving forward, we are going to continue from part C, D, E. So moving to the next question, the pin is removed and the piston settles to a position state 2. So the question is, what is the position of this piston in state 2? What are the temperature and volume of nitrogen gas in state 2? What is the entropy change of the gas, piston and copper during the transition from state 1 to state 2? So from this diagram we can see that there's a pin. So the pin has been removed. We don't know whether the piston has moved upward or downward, so we are to determine to the position it is at now. So to do that, we know that from second law of thermodynamics, we have Q to be equal to change in internal energy plus the work done by the gas or the work done by the piston. So now we have our Q to be equal to 0 because we were told that it is adiabatic in nature, and also it is frictionless. So therefore du is equal to minus W, which means our du plus W is equal to 0, but we know that our du is equal to mcv delta T, which is the same as m, that is the mass of the gas. We have the specific heat as constant volume into bracket change in temperature T2 minus T1. So we are interested in the new temperature that we have attained after the pin has been removed, and also we have our W. So now the work is actually done by the gas actually did the work on the piston. The piston moved from one position to the other, so we have the mass of the piston, going to denote it as mp, and also the acceleration due to gravity, whether it moves upward or downward, then multiply by the change in height. So this is equally equal to the mass multiplied by acceleration due to gravity into bracket h2 minus h1. So h2 is our new height, h1 is what we have obtained initially. So therefore, putting everything in the formula, we're going to have the mass of the gas multiplied by specific heat capacity at constant volume into T2 minus T1, then plus the mass of the piston multiplied by acceleration due to gravity into h2 minus h1, and everything is going to be equal to 0. So we can call this equation 1. So we have how many unknowns here? We have T2 to be unknown, and also we have h2 to be unknown. So we need another equation in order to solve them simultaneously. So again, we have our ideal gas equation. Since the system is, the gas is totally modeled as an ideal gas, we have PV to be equal to MRT. So here it's the gas we're looking at. So this is also the pressure of the gas, and this is volume of the gas, and this is also the new temperature, which is P2. So this implies that the volume, new volume of the gas is going to be area. The area is actually constant multiplied by the new height of the gas. So the new height of the gas occupied. So we have our formula to be pressure of the gas multiplied by the area multiplied by the height h2 to now be equal to mass of the gas multiplied by R multiplied by T2. So from our last equation we can make T2 subject of the formula. T2 is now equal to, we have the P2, which is the same thing as the pressure of the gas at the moment, multiplied by AH2 all over, we have the mass of the gas multiplied by R. So this is our second equation. So we can substitute equation 2 in 1. So anywhere we see T in equation 1, we can substitute it with it. We have our mg CV open bracket. Instead of T2 now we're going to substitute it with P2 AH2 all over mg R. Then we subtract it with T1. We close the bracket. We have plus mass of piston G into bracket H2 minus H1, all this to be equal to 0. So after possible expansion we're going to end up having H2 to be equal to, we have T1 mgCV plus MP mass of the piston GH1 close bracket. Then we have another bracket 1 all over, we have P2 ACV, that should be CV all over R plus MP mass of the piston multiplied by the acceleration due to gravity. So this is equal to, we have our T mCV MPGH, but we don't have this P2. So to get our P2 we're going to analyze the piston, the forces acting on the piston. Assuming this is the piston, we have the pressure, atmospheric pressure force acting on it, we have its weight also, which is mg. Then we have resultant force from the gas, which is P2A multiplied by the area of the gas. So we're told from the question that atmospheric pressure is absolute 0. So we have our pressure force, which is P2A, to be equal to the weight of our piston, which is MP multiplied by G. So therefore we have our P2 to now be equal to MPG all over the area, which is equal to 45 given from the question multiplied by 9.81 all over the area also given from the question to be 50 times 10 raised to power minus 4. So this is equal to 82.29 kilopascal. So with this pressure we can use it to obtain our H2. So after obtaining our pressure, our H2 is now equal to, we have, after substituting the values, we're going to have 1.027 meters. So this is the value of H2 after our computation. We'll find out that H2 is greater than H1. This implies that our piston moves upward. So that is the new position of our H2. It moves upwards. So now the T part of the question is we should calculate our T2. Since we obtain our H2, we can just substitute it in equation 2 by putting in our pressure, and if we do that, we are going to arrive at 204.02 Kelvin. So that is the value of our T2, and our new V2 is going to be our old volume, or our area multiplied by H2, which is now equal to our old area, which is 50 times 10 raised to the power of -4, multiplied by our H2, the one we obtained, 1.027, and this is going to give us 5.135 times 10 raised to the power of -3. So of course the volume also is going to increase because the height of our container increased. So the E part of the question, we are asked to calculate the change in entropy, which is equal to S2 minus S1. So we know that our Q is equal to 0 because it is adiabatic, and also the movement is frictionless. So we know that S2 minus S1 is equal to the entropy generated due to change of state. So that is going to be change in entropy due to the gas plus the change in entropy due to piston plus the change in entropy due to our copper. All will give us our degenerated entropy. So we know that the change in entropy due to copper is 0 because copper hasn't made any movement. It is our piston and then our gas that actually change states. So since our piston is adiabatic and frictionless, it is also 0. So we were all left with the entropy generated by the gas, which is equal to our entropy generated. So this is now equal to mass multiplied by the specific heat capacity at constant volume into ln of T2 all over T1 minus the mass of the gas multiplied by R ln V2 over V1. So this is the mass of the gas, which we calculated in A part of the question. This is CV, which is given. It's a constant specific heat capacity at constant volume, ln natural logarithm of T2, the calculated T2, which is this, all over T1, which is given from the question, minus the mass of the gas multiplied by R molar gas constant, given also from the question, ln V2, this V2 calculated, all over V1. So if you compute all that, we're going to have 2.0821 joules per Kelvin. So this is the entropy generated. This is the entropy generated. So now we look at our question. We have the F part of the question. The thin adiabatic membrane is now removed with no work or heat transfer with the environment. After some time, the system settles in state 3. So since our system settles in state 3, the temperature of the system in state 3, we are asked to calculate that, the new position of the piston in state 3, but we were told that only the thin membrane, the thin adiabatic membrane that is removed. So the piston did not move, actually it maintains its position. So what is the total entropy generated? So from all we have seen, the system hasn't make any work or heat transfer with the environment, so the system is at equilibrium. Therefore you can just use the entropy formula to calculate the change in entropy for the copper block and nitrogen block. The entire system is now in equilibrium, so we can assume that the gas is having the same temperature it's having as that of state 2 temperature, and state 3 is the same for the gas. Also, to calculate the new height, since the adiabatic thin membrane has been removed, the new height the gas has occupied now is going to also change. So just compute everything and you are going to get your new H3, and also you're going to get your new T3 for the entire system. So that is that from the calculation. So if you have any question, you can forward it or ask in the comment section. Thank you very much.